All right, let's get started. Uh, Good afternoon, everyone. My name is Qifan. Today, I'm going to talk about how to boost Spark performance on multi-core machines. And this is a joint work with my advisor, Jan Stoica, and also people at Databricks, like Samir, who is sitting there, and Reno. And also, a lot of people in the Spark SQL team also gave feedback to the project. A little bit about me. I'm a PhD student in MPlab UC Berkeley, and I'm advised by Jan Stoica. So previously, I have worked on a bunch of Spark-related research projects. For example, I worked on the geo-distributed analytics project, which talks about if we want to deploy Spark on top of geo-distributed data centers where data generated in different locations, how do we run a Spark job on top of it? And I also work a bit on big data storage systems. For example, Aluxio, which is also a project started in MPlab on in-memory storage. In a paper, we particularly tackled the problem of how do we share memory across multiple users fairly and efficiently. So previously, I also just want to mention that in the past summer, I also interned at the Databricks in the Spark SQL team, mostly focusing on Spark SQL performance improvement in places like aggregates and shuffle. And this is where I got to know those great people who give a lot of feedbacks on this project. So we started looking on how do we improve Spark's performance on multiple machines a couple of months ago. And this is still, I would say, ongoing research effort. So any feedbacks and comments are welcome here. And compared to the previous talk, we actually talk about all those different performance bottlenecks in different places and how do we deal with them with a hardware architectural approach. In this talk, I'll particularly focus on one critical component of Spark that will help us improve the performance. That is the data communication part. And to do that, we first want to understand deeply about how Spark Shuffle performance behaves. And we investigate the issue and so also give in-memory implementation of Spark Shuffle that will, as we find, improve the Spark performance by like 20 to 30% on various number of workloads. And moving beyond this, we hope to get this in-memory shuffle implementation into Spark, but this is still ongoing and there's nothing guaranteed yet. So just want to reiterate, why do we even care about many-core or scale-up machines? So as we all know, in 2009, Spark started as a research project in MPlab, which is focused at cluster framework computing. What cluster framework computing means is basically, for example, you have an analyst which types these magical RDD commands. What happens is that Spark takes the command and run it on like hundreds or thousands of machines and magically gives back the results. So I would argue one of the biggest success of Spark is basically it has achieved high availability that enables a lot of a huge range of workloads. By record, Spark by far has the largest cluster of 8,000 nodes, and also it breaks the 2014 gray sort benchmark, which means that it can get high performance when we scale out. But if we look at the typical cluster sizes that companies are operating today, this is just a quote from a senior director from Pivotal. Actually, people are running in clusters in mostly hundreds of nodes. They start by experimenting like 100 nodes and then gradually go to 200 and beyond. On the other hand, we have been observing an interesting trend of hardware development where we're incorporating more and more cores on a single chip. For example, Intel Xeon 5 chip has 64 to 72 cores on a single chip. And also at Berkeley, there's a project called Firebox, which aims to build the servers for next generation of data centers that has already incorporated more than 100 cores on one system on chip. And this is not only happening on like expensive hardware people now buying, they're also provided by major cloud providers. For example, you can easily find 32 cores major providers like Amazon, Azure, or Google. And also, just slightly earlier this year, EC2 has announced this gigantic monster X instance, which has more than 128 cores. and also 2 KB of memory. And the cost is pretty, reasonable. If you look at the individual prices, we're going to scale, it costs like $30 an hour on demand. But if you calculate, for example, the price per core, here I also list a bunch of 8-core nodes. If you compare them, it's still in the range of those 8-core machines in terms of dollar per core. It's not the highest or lowest, it's in the middle. But if you also look at the cost per memory, it actually gives you much more memory with the same price. And so if you think about it, now you have this one big node which has 128 cores and has a slightly advantage of memory, also higher network throughput intercore. And you can just use it as a small cluster to work on a bunch of workloads. So I would envision that people would take Spark and run on top of those kind of setup with one or several of those gigantic machines. But however, if we move Spark to such kind of different architecture, we will also require the software architecture to be changed very differently to work efficiently on those systems. This is because Spark was initially designed to scale well on many nodes instead of several nodes with many cores. In particular, I think there are 2 kind of critical aspects we should consider. The first thing is that the data communication, as we all know, it's called, usually we refer to it as shuffle. So Spark now store all the intermediate data of shuffle on disk when different computation stages have to communicate the data over. And this is basically because if you are sending the data across network anyway, it doesn't make sense to put them on the scarce memory those moderate nodes have. And also you have to do this serialization and deserialization when you're writing to disk or writing through the network. And many studies have shown that those kind of operations are actually the bottleneck of data communication. Now, what if we move to a more this multi-core architecture where you have much more memory to spare, and there's a lot of communication that's happening on single node, and I think you can do a lot of things. And the second aspect is resource management. I think the previous presentation also touched a bit. And Spark was designed to handle on those moderate nodes, where if we move to this current world, imagine having one executor to manage more than 100 cores and also 2 terabytes memory. Just considering the amount of GC you will hit that stop the world, it's kind of scary. But for this talk, I'm going to focus on the first one, and the second one is still ongoing work. So the immediate question is, can we actually improve shuffle on those single multi-core machines? And my answer is yes. And here the rigorous theory I'm going to give you. 1, memory is fast. Second, we can use memory for shuffle, and therefore shuffle will be fast. Very solid, right? Okay, talk is talk, and if we put this theory in practice, if you really read into the Spark's code, basically this is what happens. It does the computation and figures out which record goes to which reducer, and it takes a handle for the file stream that goes to that specific reducer and save those bytes. And then after writing to that file stream, it saves the bytes to the disk. Now, as we said, we just move to memory. So what we do is does the exactly same thing, but instead of writing all the bytes to disk, we just flush them to memory, to byte buffer that's on Java heap. And we want to test how well this solution works. So we just use a very simple query here. It's basically creating 60 million numbers and then repartition. So we actually have a beefy shuffle, and then we just do a little bit of minimum work on the reducer side. So it actually reads all the data from the map side. So we want to compare the vanilla Spark's performance with this first attempt we have here. So if you look at the numbers, actually they are just almost not, it's very hard to even to tell them apart, basically. They are very close performance and their errors are very similar. So why we have this wonderful rigorous theory that I've just shown you, but we have very little improvement here? So I went down to do profiling on the job I have just run. So this is a graph that I created with Java Flame Graph that's using Java profiling tools. And by the way, this is a very good tool I highly recommend. So basically the x-axis shows the duration of a particular method. Each box here represents a method that got executed during the job, and the length of it is basically the ratio of the time that's spent on this method. So dig really into it, you'll find this method actually corresponds the action you're writing the data into disk. And this is only 4 to 5% of the time that you spend on doing this flushing to disk operation. So basically what we found that in this particular job, the I/O throughput is not the bottleneck. It only uses 5% of the time. And we also observe that even if that we can have some jobs that where our disk is going to slow things down, in a lot of cases it can hit OS buffer cache. It means that even when we are running this disk-based shuffle, we are already exporting the memory that gives you high throughput. So how do we improve this status quo? I want to first dig a little bit into the performance model of what goes on when we run shuffle. So on the mapper side, we have a bunch of inputs, and then because we already have this powerful code generation that's in Spark SQL, it basically will collapse all the operations inside one iteration and does the work. And afterwards, it writes into a small queue, which in turn being fetched by a thread on the other side, which reads all the records in the queue and write into corresponding file streams that correspond to different reducers. And periodically, or if the writing operations are done, those files got flushed into the disk. And the reducer side is just similar, but in a reverse fashion, where we read the data from the disk and then running those operations, and it might output the final result, or it goes to another stage. Of course, I'm providing a very simplistic model here. There's more complication. For example, Spark now, the default version, uses the sort-based shuffle instead of the hash-based shuffle I'm just talking about. And also it has to consider more cases where what if you use up all your memory, you have to build some of the intermediate states into disk, or how do you clear the data after the shuffle? But just for understanding, I think that model is good enough. So if we look at this flow or this performance model, consider for the first case where we talk about that the part that's on the left side of the queue run in a single thread, and the part on the right side of the queue run in another thread. Consider a case where actually the thread 1 is much slower than thread 2. This is actually, as I discovered, a lot of the case here, because thread 1 is actually doing the heavy work of doing all kinds of different computations. And in this case, even if you can improve much on the right side to improve the shuffle performance, you're not going to speed up Spark jobs at all. And let's say if the left part is not the bottleneck, that part is lightning fast, and even though just simply replacing SSD with memory might not improve the job either, because, for example, when you're writing taking those records from the queue and writing to file streams, you're also doing many things here. You are having a lot of functions wrapped that requires to copy them into the memory because of virtual function costs, and also you have to do serialization and compression, which is shown by many studies that actually more expensive than the operations further down the way. And similarly, you have similar phenomena on the reducer side where you do decompression and deserialization that takes a lot of time. And finally, if those are not the bottleneck, then we might actually hit I/O contentions when we have a lot of the threads trying to run into disk, and they're all waiting for I/O, and then our first attempt are actually going to work in this case. So how do we improve Spark Shuffle's performance, given those breakdowns and given with those understandings? In particular, how do we, for example, solve the previous example where it's actually case 2 and things are bottlenecked on serialization and compression? Oh, sorry. So the idea is pretty simple. We have to do serialization and compression because we want to write the records out into binary format. And to get rid of that, we can just not do that. For example, because now everything is running on single node and we are sharing this piece of memory, what we can do is just create a bunch of queues and let the mappers to write all those records into these queues. And on the reducer side, we are simply passing these reference of the queues to the reducers, and the reducers can now fetch those records from those queues. The benefit of this is there's no serialization because there are still Java objects in the memory, and also there's no copy because between the mappers and the reducers, because now reducers and mappers are just sharing the same data structure. Okay, this looks promising, so we implement it and we benchmark against the vanilla Spark. And what we see is actually this goes even 3 times worse. And I don't know if you guys have some guess or have some answers. What we have find is that because we are now actually keeping all those records around, they're all being managed by the JVM, it's going to hit garbage collection really hard. And even if we subtract, for example, the 8 seconds of job collection from the job, it's still, even the blue part is still slower because now even finding one object in the JVM is slower compared to the other 2 cases where you don't keep those objects around. Okay, now the task becomes how do we get those benefits while avoiding this GC? So we have this third approach. Instead of having this one queue, we basically copy all the records into a memory page. And the records will just be laying one after another in this memory page. And the benefit of this is that now the number of objects you are keeping in JVM is not the number of records, but the number of pages. And you can simply use, for example, n by m, where n is number of reducers and m is number of mappers, pages to keep them. So this is a magnitude lower number of objects that you have to keep around. You can also do something smarter. For example, you can use only 1 page per reducer, but now multiple mappers have to write into the same memory page. I'd like to mention that this particular helps even more on Spark SQL because Spark SQL uses this unsafe row data structure for each of the record, and each unsafe row is just backed by a buffer. And when we iterate all those records on the memory page, what we can do is just use the same unsafe row object, but pointing to different offsets of the records on the main memory every time. So it gives you instantaneous creation of different unsafe row records. So we implement this, and we run it again, and indeed, it performs much faster compared to vanilla Spark. And if you go providing this, you'll find that the improvements come from all those different tiny bits, and it's much different than what we imagined that all the improvements will come from the increased throughput from disk to memory. And because a lot of improvements actually come from things like serialization, deserialization that actually are CPU bound, and we can have pretty consistent improvement with varying size because the improvement actually happens for each record when we run the job. For example, here when we use the same sample job again by varying the number of records, we can see the improvement is pretty consistent. So to test out in a more real workloads, we tried out on TPCDS, which is a database benchmark, and on a single node. And we just take the first 33 queries and run it and find out actually 27 out of the 33 queries will improve with the median improvement of 31%, which is pretty promising. So far I have talked about in-memory shuffle implementation we presented, and we show that it improves on a single node. Of course, I mean, you cannot run all those workloads on just one 128 core node. So how do we extend it to more multiple nodes that can support more workloads? So the extension is quite simple. We just still write all the data goes to memory. And for shuffle that happening across nodes, we just copy from the memory page to network buffer. Compared to actually a more memory preserving way where we kind of try to write the data that will goes to remote shuffle into disk, it will be harder to manage because now you have to enforce stricter locality on reducers, and also you might not get those benefits of avoid I/O contentions. The way we go with the first implementation is we assume we have the luxury of infinite or enough memories that we will just use them as a gift. So we run a simple shuffle job again, but now on four different nodes, and we find that with map we can have pretty consistent improvement because now they are all writing to memory and getting rid of those overhead. And with reduce, also it works as our intuition. When you have more nodes, the improvement decreases because now you have more remote shuffle that basically makes you don't get the benefit of sharing the data inside one node. We also try the TPCDS on the 128 core X1 instances. So unfortunately, I haven't had the time to run very comprehensive all query benchmark. But here is we use the TPCDS dataset with a scale factor of 100, which is around 30 gigabytes of data, and we pick just the top 5 queries from the single node experiment, and this plots the results of best of 10 runs, and shows that we still have some improvement, but compared to the single node, the improvement is much less. The hypothesis here is that there are many other performance bottlenecks that will go into running Spark on this 128 core with 1 GVM, and things like GC and thread imbalance that slow things down. So in summary, I have argued that Spark on many core architectures will require some software changes to fully realize the potential. And in particular, I have talked about in-memory shuffle, which is a part of the solution we have give to work towards this direction. And we have shown that there you can get like 31% improvement on Spark for certain workloads. And going on, we want to identify other performance bottlenecks in this direction. And this concludes my talk, and I have to take any questions. Thanks.
All right, do we have any questions? I see one in the front row there.
So one of the biggest improvements in terms of stability in Spark 1.6, I believe, was the introduction of shuffle service,
Okay.
and that decouples the management of a file shuffle result and the Spark process itself. But what you're doing there is going to bring back the data back into the same process of the executor process.
Yeah.
Have you thought about the stability, the implication of the stability? Because shuffle service wouldn't work in this case anymore.
Yeah, I think a lot of the techniques and also approaches that we're using here will also apply to shuffle service. But this is, as I said, this is basically a kind of initial exploration that gives us confidence of where the bottlenecks are and where we can improve things. And I think in the long term, there will be more kind of comprehensive solutions. And we can also I also have some other ideas. For example, you can provide a more shared memory, memory abstraction across nodes. Yeah. There are a bunch of research projects that are working on this direction as well. Yeah.
Other questions? All right, let's give one more round of applause.